All right, good morning or good afternoon, AP Calculus class. Obviously, I am not in class today, and I am hoping that you are having a wonderful day today with the sub. At this point, you should have written your reflection for me through Google Forms about the most recent exam that you guys took last week. And you should have gone over the project that I also posted to Google Classroom. Okay, so if you haven't done those things, go back and do those things for me first. For the rest of us, I'm going to just start in on section 4.2 today, which is going to be all about the mean value theorem. Okay? So everything today is going to be about the mean value theorem. We're going to cover this fairly quickly. I really just want us to get the theory behind the mean value theorem kind of down into our notes. And we will look into a little bit more on the practicality and the applications of the mean value theorem, when I get back to school on Tuesday. So let me get a little more light in here and make some quick adjustments. And we will begin to talk about this mean value theorem. Okay, so we've seen big theorems before. The two big theorems that we have talked about so far have been the extreme value theorem and the intermediate value theorem. And the mean value theorem is going to work in a fairly similar manner in that we are going to have conditions that need to be met in order to use the mean value theorem, and we're going to apply the mean value theorem to different situations within the calculus. All right, so let's start about our conditions. So in order for us to use the mean value theorem, f must be continuous on the closed interval between a and b, and f must be differentiable on the open interval between a and b. Okay? So not only does f have to be continuous this time, f also has to be differentiable. Okay? Well, what does the mean value theorem say? The mean value theorem says that if both of these ideas are true, that the function is continuous and differentiable, then the following must happen. F of b minus f of a, all divided by b minus a, is going to be equal to f prime of c for some c on the interval in between a and b. And what we'll do is we'll look at this graphically as exactly as to what this means. But again, all the mean value theorem says, that is, if f is continuous and on the closed interval, differentiable on the open interval, then it must be true that whatever f of b minus f of a divided by b minus a is equal to f prime at c. Or the slope of the secant line that connects our endpoints must be the same as the derivative for some value in between the endpoints. Okay? So let's kind of look at this graphically because I think that will help us. Okay? So let's imagine we have f here, which is just going to be some curve. Well, we're going to bound f between a and b. We're going to recognize that f is continuous on AB, and f is differentiable on AB because we can tell that there are no corners or cusps, or f is smooth enough. Okay? All right, so if I look at f of a, that's going to be our function value. If I look at f of b, that's also going to be our function value. And if I were to draw the secant line between a and b, we'd have some tangent line. Okay? It's this tangent line created by the endpoint. In fact, if I wanted to find the slope of that tangent line, maybe we'll call this line L, and I want the slope of this line L, well, we would take f of b minus f of a, divide that by b minus a. Okay? That should look familiar. That should look familiar back to from our original definition of the mean value theorem. There it is. We see it, f of b minus f of a divided by b minus a. Okay, so there is kind of the left-hand side of the equation that accompanies this theorem, states the slope of the secant line between 2 points. Okay. Well, what is it that the theorem guarantees? Well, the theorem guarantees that if f is continuous and differentiable, then some point in between a and b, the slope of the tangent line is going to be parallel to the slope of the secant line. Or excuse me, the tangent line will be parallel to the secant line, or the slope of the tangent line would be parallel to the slope of the secant line. And we could see geometrically that in this case that this happens, roughly about right here. And notice that we map back to this value of c. We map back to this c value that is trapped in between a and b. And the slope of our curve at c is exactly the same as the slope of our line L, which was the line that's connected by our endpoints. All right. So, in conclusion, we find that f prime at c must be equal to f of b minus f of a, all divided by b minus a. Okay? And that's really what I want us to get from this today. Okay? We will extend the ideas on this. We'll see where this comes from, using a very particular case that we will end up calling Rolle's theorem. But again, for today, in your notebooks, I need you to know that the mean value theorem has the following conditions. It has the following hypotheses: that f must be continuous on the closed interval between a and b, and f must be differentiable on the open interval between a and b. If that's true, then f of b minus f of a divided by b minus a, or the slope of our secant line, must be the exact same slope that we have when we take the derivative of f at some value c that is bounded on our interval between a and b. All right, so make sure that gets in your notes. We will see you in class tomorrow.